start recording. Okay, so today's topic is the metric space. So remember last time we proved all norms on Rn are equivalent. That is a statement about vectors. So I think we're pretty good on the metric space of vectors, right? Now we want to go up to the metric space of linear transformations. Okay. Now, you should have seen in linear algebra that if you get two vector spaces, then actually the linear transformations between them are themselves a vector space. Okay, and if you didn't see that in linear algebra, you saw it a few lectures ago in this class. So let's introduce some notation for it. I can't remember if we had this notation back then. So let's trying to remember how to draw a fancy L. I'll just draw a non-fancy L. In the notes, it'll be fancy. Okay, so L, Rn, Rm be the set of linear maps from Rn to Rm. Okay. Now, back the first lecture that we did on linear algebra, we said that we can identify these linear maps with matrices. Okay, so we've seen that this space can be identified with the set M. Okay, and remember, things get flipped in terms of the dimensions. They kind of get flipped. So these things map from Rn to Rm, and therefore they are M by N matrices. Okay, so everybody remember when we did that a few lectures ago. Now that process actually does involve picking a basis. Okay, now in this course we're always using the canonical or the standard basis, but there is a choice in there. But anyway, I mean, this gives us an isomorphism, really, between these two vector spaces. The vector space of linear maps and the vector space of M by N matrices. Okay? Now, you may recall from linear algebra that all vector spaces all finite dimensional vector spaces of the same dimension are isomorphic. So these are both isomorphic as vector spaces to R to the M times N. Okay. This word isomorphic, I mean, we're not really going to use that word here. Or we don't care about all the extra stuff that entails. All I'm really trying to say is that you can view, we said above, you can view a linear transformation as a matrix, And now I'm saying you can view a matrix as a vector, okay? It's just a big vector, and it happens to be a rectangle instead of a line, okay? Now, we have plenty of norms on vector spaces, so we can apply those norms to matrices. Okay, right? We can apply vector space norms to MMN. Okay, because MNN is just a vector space, and we view it as our MN, and then we can use any metric we have there. So, for example, we can define the 2 norm here. Okay, the 2 norm would be exactly what you expect. So long as you're looking at a matrix capital X, which is m by n. Okay. And we don't even need to say prove it's a norm. We've already proved it's a norm. It's a norm on the vectors, so it's a norm on the matrices, because matrices are just rectangular vectors. I mean, we can view them just as rectangular vectors. Okay. So we are in a different context, though. So when we are looking at the 2 norm on matrices, it's called the Frobenius norm. Okay. Now, it's a perfectly fine norm. And we proved last lecture that all norms are equivalent, so any other norm we come up with would also be a norm on RMN, so it would be equivalent to this. So you might wonder, why don't we just use this norm? The problem is, if we want to think about linear transformations, okay, let me give you a linear transformation. I mean, T of x1, x2 equals, I don't know, 3x1 plus x2, 0, x1 minus 2x2, something like that. And I say, what's the Frobenius norm of that linear transformation? Okay, what would you have to do? You'd have to convert that thing into a matrix, choosing a basis. Well, I mean, okay, so if we're going to talk about you'd choose the standard basis. But anyway, you'd convert it into a matrix. And then you have to do this 2 norm thing, okay? And then the real problem is you'd get a number, which is the Frobenius norm of that transformation. But that number wouldn't really mean anything in terms of the transformation itself, okay? I mean, we could prove some theorems about how that number might relate to how large the result of or an image of that transformation might be. But it's just not really capturing anything about the transformation itself. It's capturing something about the matrix representation, okay? So that's the Frobenius norm. We've already got it. The norm we're going to define is equivalent to it, but the norm we're going to define is not equal to it, and the norm we're going to define is better for applying to linear transformations. Okay, so that's the point of today. We want a better norm for linear transformations. Okay. We're going to start out in a fairly general context. So we're going to have a map from Rn to Rm, and we're going to allow ourselves to have any two norms on Rn and Rm. Okay, so that's what we've got. We've got two norms. Our result is going to say that for any linear transformation T, it can only scale vectors by so much. Okay. So I'm not a huge fan of this notation of these double bars, sub r to the n and sub r to the m, but I couldn't come up with a better way to keep them separate. The point is we've got those two norms, one on the domain, one on the codomain. We've got this linear map. We're claiming that there is this constant C, such that C bounds how large we can scale a vector x. And I haven't specified which norm we have here. Okay, that's a good exercise to think about. The norm on x is the norm in Rn. That's the norm in our domain. And then once we've applied t to it, we're in Rm. So we need to apply that norm there. Okay. And remember, those are standing in for any two norms you might want on those two spaces.
Dr. Otter?
Yeah.
So this is really just an upper bound, right? Like this transformation could scale this vector, really, 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 really small.
Mm-hmm.
Or I guess bigly negative.
It's not going to scale at negative.
Oh, right, because the norm.
Yeah.
Right. Okay.
Yeah. I mean, but of course it could send a bunch of vectors to zero, right? If it's not a full rank linear transformation, it's going to be sending non-zero vectors to zero. Okay? That's what not being full rank is. Okay? Now, if you think back to last semester, frequently we needed to show that a set was bounded before we could do something to it. Well, we're showing that there is a bound here. Okay, and then our next result is we're going to use that to do something. Okay. But yeah, this is just, there is some bound on how much every linear transformation can scale a vector. Okay, the proof I mean, the proof might look a little bit strange to you because you're not used to proving things in normed vector spaces. But it is a completely standard proof for working in a normed vector space where we're just going to look at what it does to the basis vectors, and then we're going to appeal to like norm axioms and vector space axioms and linear transformation axioms to translate that back to get our results. Okay? Let's define M to be the maximum of the norms of the images of the standard basis. So our domain is Rn. There are n standard basis vectors. And we want to take the norm of their images in Rm because that's where they get mapped to. Okay. Now, another standard trick, we just kind of, let a point in the domain be arbitrary. And we write it in terms of this standard basis. And again, when we do this, those x sub k's are they're just the components of the vector representation if we bother to write it as a vector. Okay, and now what are we interested in? We want to know the Rm norm of the image. Okay. Well, by the linearity of T, we can write this. We can write the image as a sum of scalars times images of the standard basis vectors. Okay. Now, the triangle inequality on this norm right here, on whatever norm we're looking at in Rm, that triangle inequality says that the norm of a sum is at most the sum of the norms. Okay, and I want to do one more thing at this step. We also know that, because we're dealing with a norm, that scalar can come out as long as we give it an absolute value. So this is less than or equal to the sum of the absolute values of the xk times the norms of the transformation applied to the standard basis vectors. Okay. Okay, now, where did we do it? Up here. We defined M to be the maximum of all these norms of the images of the standard basis vectors. So we can use that upper bound here. Okay. Now, what is this?
It's M times the one norm in Rn.
Mm-hmm. Yeah, which we'll just denote by 1. Okay? Now, is that good? We've said that the norm of our linear transformation applied to x is less than or equal to capital M times the 1 norm of x. Have we proved the result?
Almost.
Yeah, almost. What's wrong is we don't have the right norm on x. We've got the 1 norm. We want, I don't know, this arbitrary Rn norm, Rn norm that we started with. Okay, but now you remember the result of the previous lecture. All norms are equivalent. Okay, so up to a constant factor, we can just replace that norm. Okay, so because the 1 norm on Rn and whatever norm we started with are equivalent, there is a constant, let's call it k, because there's a c in the statement of the theorem, greater than 0. So we're only really using half of the equivalence here. We're only using the half we need. And what's true, such that what I really want to say, because we've already defined x to be arbitrary, so I really want to say that this is true. Okay. And therefore, we've got what we want. T of x okay, so that proves the result where C is equal to M times K. Any questions on that one?
I've got a question kind of about our setup.
Mm-hmm.
So here we get this nice M because we have a finite dimensional
Mm-hmm.
space. Suppose we had some sort of infinite dimensional, do we get to take like a supremum instead and similar things?
Mm-hmm.
Follow?
Yeah.
In algebra, a lot of things broke in infinite dimensions.
Yeah, this breaks too. So what we've just proved is that in our nice finite dimensional spaces, all linear transformations are bounded. Okay, this is the definition of a concept called bounded. We're not going to make that definition because all of ours are. So we're in this great world of bounded linear transformations. When you go up to infinite dimensions, you actually want to restrict to the linear transformations that satisfy this proposition, right? You restrict yourself to the set of bounded linear transformations.
Okay. Because I'm just thinking about like a Taylor series as a transformation, and that's, you know, you have all the higher order terms. So, you know, I'm thinking that like it'd be useful to apply to stuff like that, I guess, is what I'm thinking.
Mm-hmm. I mean, yeah, there are plenty of unbounded linear transformations if you have an infinite dimensional domain. Okay. But we don't. We're going to stick to finite and many dimensions. We'll leave infinite dimensional calculus for a later course. Okay. Okay, so we got this result. It says, well, like we were just talking about, it says for any linear transformation between two finite dimensional real vector spaces, there's a limit to how much that linear transformation will stretch a vector. Okay? I mean, and that limit depends on the transformation, of course. The stretching limit that we just found also depends on the two norms that we want to put on the domain and the range. Okay. Okay, now what we're going to do is we proved this result in this extreme generality of any two norms. Now we're going to specialize, we're going to have the two norm everywhere. So the two norm on the domain and the two norm on the codomain. So this is nice, this is linear transformations between Euclidean spaces. Because remember, Euclidean space means Rn with that two norm. Okay. So again, now we specialize to Euclidean space. Rn with the two norm. Well, D2 is the metric that comes from the two norm. Okay. So, given transformation from Rn to Rm, we define, okay, and if you remember back to the beginning of the lecture, the whole motivation is we want a norm that's based on operators, and so it's based on transformations rather than based on matrices. So this is called the operator norm. Okay. This is the smallest of the constants that work in the previous results. And of course, like I said, we're just considering two norms now. Okay, so what our previous result says, I misspoke earlier. I said our previous result will say that a set is bounded. It doesn't. What our previous result says is that this set we'd like to take the infimum of, is non-empty. Now, to take an infimum, we need a couple conditions. What's the other one?
Bounded from below.
Yeah, we need bounded
We have
below.
0, right?
Mm-hmm. Yep, we have 0. We couldn't.
I do have a question about this norm.
Mm-hmm.
In the previous proof, our constant depended on our choice of basis. Does that mean that this norm depends on a basis choice as well?
That's what's even better about this norm. There's no basis choice here. Okay. So this has a property that's known as like coordinates independence. So it does not matter the basis you pick, which really means it doesn't matter the coordinates you're working in. Does that make sense?
I think.
So when you change your basis, when you change your, instead of saying change your basis, let me say when you change your coordinate system, which is kind of the same thing. When you change your coordinate system, your two norms of your vectors don't change, okay? But the actual matrix that corresponds to your linear transformation does change. So its Frobenius norm depends on the coordinates you're using. This operator norm does not. And that's a big reason to favor the operator norm. Okay. The other nice thing about the operator norm is it tells you something about the linear transformation. It tells you how much it's stretching things. Okay, which is a lot more useful than telling you something about, the square root of the sum of the squares of the entries in the matrix that corresponds to the linear transformation. Okay. Okay. So let's see, we've got 15 minutes left. The obvious next proposition is that this really is a norm. Okay. Well, you got to check the 4 properties. The first 3 are pretty easy, as usual, when you're proving a norm. Remember, the first one is that it's non-negative. This is always non-negative. 0 is a lower bound on that set. The second one is that the only place it takes on the value 0 is at 0. Let's talk about that for a second. So we need to prove that t opt equals 0 if and only if t equals 0. Okay, now there's 2 different zeros here. This is our familiar real number 0. The second one, though, is the 0 transformation. And the 0 transformation is the transformation that maps every vector to the 0 vector. Okay, or it would be the transformation whose matrix is just all zeros. Okay. Well, how do you prove this? If you've got a non-zero linear transformation, then there must be some non-zero vector that it maps to something of positive norm. And then that allows you to show that this infimum cannot be 0. Okay. And then, as usual, the only slightly difficult part about this problem, about this proposition, is the triangle inequality. And I will save that fun for the lecture notes, because we've got one more result to look at, okay? So, in the lecture notes, you'll find a complete proof. Once they're written, you'll find a complete proof that this operator norm really is a norm. Here's the theorem I'd like to end with to that. Which gives us a nice alternative way to look at that operator norm. Okay, so instead of thinking about it as the infimum of the constant c that work as an upper bound on the stretching factor, here we see we can look at it instead as the supremum of the norms of the images of, recall, this is the unit sphere. This is the set of all points of 2 norm 1. Okay? Now, we have proved that linear transformations are continuous, and we've proved, this is from the last lecture, we've proved that the 2 norm is actually continuous. Okay? The 2 norm viewed as a mapping from a vector space onto the real line. That's a continuous function. Then if you think back to very early in this semester, we proved that you can compose continuous functions. Okay. So, the mapping, that's proof. The mapping f of x, or how about I just do it this way? The mapping f, defined from the unit sphere into R, defined by, take the 2 norm of the transformation applied to x, okay, is continuous. Now, what we should really do is say what metrics we're using, okay? Because unfortunately, today's lecture we've used a bunch of metrics. So this is continuous as a mapping from let's see, we're looking at the mapping from the unit sphere with the D2 metric. To the real line with the standard metric. Okay. Since the unit sphere is compact, you know, in I guess we can say that in Rnd2, although, well, anyway, F attains its supremum. So let's give it a name. Let's let M be the supremum of F. And again, we're just thinking about F as a function on the unit sphere. Okay. And we'd like to give a name to the point where F does attain this supremum. So let's let F of X naught be M. Okay. Now, that's really just the setup. We've got the supremum here. We have said it exists. Well, obviously it exists. We have said it's attained. So really, we could put right there. We could put a max, because it is the maximum value of F on this. Okay, but our question is this really the same as the operator norm, which we have to define up here? Okay. Well, we're going to do two inequalities here. First, we are going to say that any vector in Rn is stretched by at most this factor m. Okay? So first, for every non-zero vector y. Okay, now we play our standard game, which is just we pull out the 2 norm of y, leaving us with a unit vector, which is on the unit sphere, and then we use this bound. Okay, so completely standard tricks. We want to know the 2 norm of ty. This is a mess here, but it's not all that complicated. We pulled out that scalar. Okay, to pull out that scalar, we just divided by it. Okay, the reason we can do that, well, I mean, we need 2 arguments for this, okay? The reason we can get it outside the t is that t is linear, and the reason we can get it outside the norm is the norm axiom that says that scalars can come out with an absolute value, but of course we don't need that because it's already a norm. so it's non-negative. Okay, and now we've got the two-norm of y times t of something on the unit sphere. Okay, and the two-norm of t of something on the unit sphere is at most m by assumption. Okay, so this shows that this infimum right here cannot be more than m. Okay, because if it were more than m, well, let me put it this way. M works. M satisfies this condition in the set. So M is in this set. Yeah, there. That's the easy way to see it. M is in this set that we're taking the infimum of. So, of course, the infimum can only be less than M. Less than or equal to M. And we want to claim it is equal to M. Okay? So, now we only need to show... Well, let me write that down. This implies that the operator norm is less than or equal to capital M. Okay. For the other direction, if we have a constant C in that set, so okay. If this is true, then it must be true at x naught. Okay. So at x naught, we know that put my 2 in the wrong spot there. Okay, at x naught we know that we have this. So if we had a C that worked for all x, then it would have to work for x naught. Okay, and to work for x naught, if I plug x naught in here, the only constants that are gonna work are things that are at least m. Okay, so we said M is in the set, so the infimum can only be smaller. And, oh, sorry, Benjamin, I didn't see your chat until after I corrected it. But anyway, we said M is in the set, so the infimum can only be smaller. Then we proved that everything in the set is at least M, so the infimum can only be bigger. And of course, by smaller and bigger, I mean weakly smaller and weakly bigger. So that proves that the infimum is equal to this supremum. Okay? So now, that's it for today's lecture, but from now on, this is really kind of the most useful definition of this operator norm. Okay? It's just the largest 2 norm of an image of the unit sphere. Okay? So, have a great rest of the day, everyone. and I will see you on Friday.